While the continuity equation for an incompressible fluid is essentially the result of conservation of mass, we now derive another relationship for steady flow where the work-energy theorem describes the relationship between speed, pressure, and elevation of an incompressible and non-viscous fluid. This result is known as the Bernoulli equation, which was discovered by the Swiss mathematician and physicist Daniel Bernoulli. Recall from Chapter 6 that the work-energy theorem states that the net work done on an object by external non-conservative forces is equal to the change in the total mechanical energy of the object. We have to use this general form of the work-energy theorem since the collisions in a fluid that create its pressure are non-conservative. To begin, let's first look at a fluid flowing through a horizontal pipe with a changing cross-sectional area, as was the case for the equation of continuity. As the fluid flows through the section of pipe with a reduced cross-sectional area, we know the speed of the fluid increases. But now let's consider the pressure in the pipe. In order for a volume of fluid to speed up in the reduced cross-sectional area of the pipe, an unbalanced force must accelerate the fluid in the direction of motion in accordance with Newton's second law. This force must come from a difference in pressure within the pipe. Specifically, the pressure in region 2 must be higher than the pressure in region 1, as the gauges in the figure indicate. We will see that this difference in pressure is given by Bernoulli's equation. Second, we also need to take into account any changes in elevation of the pipe. If the fluid moves to a higher elevation, the pressure at the lower level will be greater than the pressure at the higher level. This observation results from our previous studies on static fluids, and Bernoulli's equation will confirm this, assuming the cross-sectional area of the pipe remains constant. To derive Bernoulli's equation, let's consider the following figure, where fluid is moving through a pipe that is changing its cross-sectional area and its elevation. The speed, pressure, and elevation in the lower region, region 2, is given by V2, P2, and Y2. Likewise, the speed, pressure, and elevation in region 1 at the higher level is V1, P1, and Y1 respectively. As discussed in Chapter 6, the total mechanical energy of an object is a combination of a kinetic energy part and a gravitational potential energy. When work is done by external non-conservative forces on an element of fluid, the total mechanical energy changes in accordance with the work-energy theorem. The following figure helps us understand the origin of the non-conservative work on the fluid element. The top surface is surrounded by a fluid at a pressure P, giving rise to a force P times A, where A is the cross-sectional area of the pipe at that location. Below the fluid element, the fluid exerts a slightly larger pressure, P plus delta P, where delta P is the pressure difference between the ends of the element. As a result, the force on the bottom is delta F equals P plus delta P times A. Therefore, the magnitude of the net force pushing the fluid element up the pipe is delta F equals delta P times A. If we consider a short length of the fluid element to be S, then the work done by the net force in moving the fluid through a distance equal to this length would be delta F times S, or delta F equals delta P times A times S. The quantity A times S is just the volume element V of the fluid, so that the work done is just equal to delta P times V. The total work done on the fluid element in moving it from region 2 to region 1 will then just be the sum of the small increments of work delta P times V as the fluid moves along the pipe. This sum amounts to P2 minus P1 times V, where P2 minus P1 is the pressure difference between the two regions. Using this result for the work done by the non-conservative forces, we can write the work-energy theorem in the following way. By dividing both sides of this result by the volume V, we pick up factors of m over v on the right side, which is just the density of the fluid. Rearranging these terms, we finally arrive at Bernoulli's equation. In the steady flow of a non-viscous, incompressible fluid of density ρ, the pressure P, the fluid speed v, and the elevation y at any 2 points are related by the following expression. Since the points 1 and 2 were selected arbitrarily, the term P plus 1/2 ρ v squared plus ρ gy must have a constant value for all points in the fluid. Notice that for the case of a static fluid, V1 and V2 in Bernoulli's equation would be equal to 0, and it would reduce to P2 equals P1 plus ρ gy, which is the result we obtained in a static fluid for pressure as a function of depth. Furthermore, if the fluid is moving, but the pipe has a constant cross-sectional area, then V1 will equal V2, and Bernoulli's equation again reduces to the same result.